Heidi, and I will be your web event specialist today. At this time, I would like to welcome everyone to today's web conference. All lines have been placed on mute to prevent any background noise. And please note that today's web conference is being recorded. We will have a question and answer session during today's presentation. You may submit questions at any time. Locate the Q&A option in the floating toolbar at the bottom of your screen. Click on the Q&A icon to open the Q&A panel on the right-hand side of your screen. Type your question in the open area and click Send to submit. If you experience any technical difficulties during today's conference, please use the chat box on the right-hand side of your screen to speak with me directly. Locate the chat option in the floating toolbar at the bottom of your screen. Click on the chat icon to open the panel on the right-hand side of your screen. It is now my pleasure to turn today's program over to Chris Heideck, Category Strategy Manager. The floor is yours.
Thank you, Heidi, and hello, everyone. Before we get started, we'd like to wish everyone well in managing through the current crisis and in your planning for the next and new normal. And thank you for giving us your time today regarding our webinar on machining optimization for exotic materials in aerospace, hosted by MSC and Sandvik Coromant. My name is Chris Heideck, Category Strategy Manager with MSC, and I have the pleasure of introducing today's presenter, William Durow, Aerospace Specialist and Global Engineering Project Manager at Sandvik Coromant. William has held a variety of technical and leadership positions within his 30 years in manufacturing. In his current role, William serves as manager for the Global Engineering Project Office, supporting the aerospace industry. William manages a team that oversees complex customer projects all over the world, helping customers optimize their operations and making their business better. William holds a manufacturing and mechanical engineering degree from the New Jersey Institute of Technology. Again, thanks for joining us today. We hope you find value in today's session, and we'll turn it over to William to begin the presentation.
Great, thank you, Chris. I concur with Chris. In lieu of today's environment, the world we live in today, I want to thank everyone for their time today to listen to us and some of the things we can hopefully teach them what they could do in their manufacturing facilities to make them more productive and more efficient. To start, I think it'd be good to start with a little poll question, Chris. If you look at the industries today and looking at automotive, today, if you look at an automotive engine, can you guess about how many inserts it takes to make an automotive engine? It takes about 4 inserts. For our poll question today, can anyone guess how many inserts it takes to make an aircraft engine? Heidi, do you have our poll question, please? The reason we asked this is the industry today, there's a lot of challenges. Many of the challenges we're going to see is on the different materials, which we'll talk about in more detail. So the answer to our poll question is actually 3,000 inserts. It takes about 3,000 inserts to make an aircraft engine. The reason for that is the materials we're seeing. If you look at automotive, for instance, many of the materials we're dealing with are steel and cast iron. But in aerospace, we see mainly what we call IOS types of materials. This consists of HRSA materials, which are more or less the nickel-based, cobalt-based, and iron-based, as well as titanium-based. And they create many different types of challenges for us. So looking at the different challenges we have, the biggest is the machinability. When you look at these materials, some of the characteristics are strength at retained high temperatures, which gives us a lot more cutting forces required to machine these materials. Higher dynamic shear strength, so you need more power to actually shear those materials. And most importantly, poor thermal conductivity, which we'll talk about a little bit more later. So essentially what happens is these materials are designed to resist heat. They're in aerospace engines. They're designed for that. So what happens is the bulk of that heat doesn't necessarily go back into the cutting chips that we make. It actually goes back into either our components and or into our inserts, which becomes challenging, which we'll talk about further. Materials are hardened, which gives us more tendency for notch wear, which we'll talk about further. The surfaces are prone to work hardening, which creates other tendencies of notch wear. And then some of the materials actually have hardened carbides in their structure, which creates challenges with abrasive wears. Some of the things we can do is we can change the insert requirements. We can go with more positive rake inserts, smaller edge preps, sharper inserts, inserts with smaller land. The grades or lower cobalt to incorporate the hot hardness we have to deal with. Tougher edge lines, and then coating adhesion. So these are the things we want to look at when we're dealing with these types of materials. Other challenge we have is the condition of the materials. There's different types of materials out there which are bar stock, they're roll formed, they're forged and or casted. And you can see from the chart above, different machinability rates are different. So if you get a cast material, there'll be a lot more difficult machine than a bar stock, and we need to take consideration when we're selecting the proper tools we're going to use. The other thing we need to look at is the effects of hardness. What are those materials' hardness levels? Are they annealed? Are they solutions treated? Or are they aged? Softer materials typically require tougher grades, whereas the harder materials will require more wear grades. And you'll get more heat buildup, and you'll need those more wear-resistant grades. When you're looking at the hardness of these materials, you need to take that into consideration as well, and the different processes it goes through. For instance, if you take a piece of 718 that's annealed, basically the stresses to create a chip, you're going to be about 900 pascals. Whereas if you have something that's actually aged hardened, 718, same material, just different treatments, you're going to be upwards of about 1350 megapascals. That's about a 40% increase. So what does that mean? You're going to have to approach this material slightly differently. Different techniques, different grades, different types of geometries. When you look at the different HRSA materials, there's quite of a variety out there. The focus we're going to talk today mainly about is the nickel-based. But keep in mind also there's iron-based and cobalt-based. Iron-based, a little bit heavier. They have an iron base to them. They also have nickel in them. You'll typically see them on shaft-type materials. You are starting to see a little bit more of the cobalt base, but cobalt is typically seen a little bit more in the medical field. So we're going to focus a little bit more today on the nickel-based materials. Most common is 718 Inconel. We also see Waspaloys, Utimets. We also see some more of the proprietary materials, the Rene materials, R1000, PRM48, and ME16 type materials are also out there. And special needs are looked at when we need to machine these materials, which we'll talk about. Next area is the titanium group. Titanium is typically about 60% the density of steel, very light, very excellent corrosion resistance. They're formed in two different types of areas, the alpha and the beta stages, which we'll talk about. Most common we see in the industry today is your 6AL4V. That's the most common, and we'll base a lot of what we talk about today on that material. When we look at the different structures, we have your alpha crystal stage. They are typically a lower density, a lower strength material, higher creep resistance, and a little bit better on the machinability. And then you get your betas, higher density, higher strength, lower creep strength, poorer machinability. And then you have the mix of the two. So if you look at your alpha beta mix, this is where your TIL 6Al4V sits, your very common titanium that's in the industry today. When you look at the various types of titaniums, again, the alpha, the beta, and the alpha beta mixes, you can see the speed factors to the left on the chart. The most common one, as I mentioned, is the titanium 6Al4V, which I just highlighted. We like to use that as a speed factor of about a 1. And what I mean that about speed factor is the cutting speeds we use to machine these types of materials, whether you're turning, milling, or drilling. And what we want to do is, as those materials go farther down to the beta alloys, we saw we need to actually decrease our speed. So if you're looking at a material more in lines of a 5553 or a 1023, which is more common in, I'd say, structural landing gear type materials, we want to reduce our speeds. And all that's done by the different alloying factors and the crystal structures that develops these materials. Now that we've talked about the different materials we're looking at, next I want to talk about the process. Proper planning of your processes is important. And when you're looking at a component, you want to start by analyzing the features. We don't want to go right into picking speeds, feeds, grades, and geometries. We want to look at our features, put an analysis together, and find out how we want to approach that. Put a machining strategy together, then get into picking your right cutter selection, then get into cutting data, and then get into your programming techniques. We don't want to jump right into programming techniques and speeds, feeds, and grades. You wind up creating challenges for you in the long run. The other thing is we want to look at is it's understandable in the aerospace industry when we look at existing production that sometimes it's a challenge to make changes. Reason being it's a locked process. So it's very difficult to make your changes in there. Then you have your partly open, which maybe you're investing in a new machine and you have an opportunity to make some changes inside the production. And of course, then you have your new production, which you're free to do pretty much what you need to do during the production phase. So find out where you are in the production phase and then see what changes you can make and the different things you can apply as we talk today. So typical challenges we're going to see, some of these we've already mentioned, is the forge and cast skins. We're going to talk about techniques we could use to get around those. Chip control. Many of these materials we look at today have challenges in breaking chip, primarily in the turning and drilling applications. Chip evacuation, when you're creating pockets or deep cavities, removing chips out of there is sometimes a challenge. Short tool life. Dealing with these materials is you're not going to get the tool life you're going to see typically in machining aluminum, steels, and cast irons. So a lot of techniques need to be applied to look at that for more process security. Secure process. We're dealing with very expensive forgings and castings, so we want to have proper security when we're machining these components. Close tolerances and surface integrity. Many times in these critical components, we need to be very careful with the tolerancing and the surface integrity on these different materials. We don't want to get any work hardening. We don't want any micro cracking. We don't want any white layer inside of these components. So different techniques need to be applied to help compensate for that. The chip formation is one of the most important things when it comes to machining, particularly in the turning applications. Typically in turning, when we're creating the chip, the heat goes into the chip. The challenges we have when we're dealing with these types of aerospace materials is the heat doesn't necessarily go into the chip. They are heat resistant material. They are designed to resist the heat. So what happens is that 80% of the heat that typically goes into our chips, if you take a piece of 4140, for instance, and you're machining it, when the chip comes off, it actually turns a blue color. That's because the heat is being brought away inside of the chip. In these aerospace materials, that is not the case. The heat actually is increased to about 80% of that goes into our inserts, which creates challenges. So what happens is we have these challenges we need to deal with when it comes to tool wear, which we will address. Some of the things we could do is we can look at the different insert geometries. So one of the things with these materials, they like to be sheared, they like to be cut. So typically what we want to do is we want to go with a sharper geometry. Some instances uncoated, titaniums work very well in uncoated inserts, for instance, or very thin PVD coated. We like to use direct press sharp inserts, or we like to use something that's peripherally ground sharp inserts. Again, these materials like to be sheared. If you get something more with a negative type geometry or a larger edge preparation, what happens is it creates heat during the cutting operation. You're actually plowing or pushing the chip. You're not actually shearing the chip. So what happens is you're actually building up heat inside that cutting zone, which is actually being a detriment to you in your process. What happens when you build up the heat? You're going to have specialized tool wear, which we'll talk about. You could create stresses in the materials. You can create white layer. You can create work hardening of those materials. You can create micro cracking in those materials. So we want to be mindful of that. Again, sharper is better. Again, you look at this picture we have up top here. Again, looking at the sharper geometry. I mean, sometimes we can get away with using positive geometry, but sometimes we still need to use a negative geometry. But be sure that we're using something that has a sharper tendency or has a periphery ground. They will perform much better in these types of materials. If you can see from the illustration here, when we're pushing that chip, we're getting a nice shear, as to opposed of when we're using a negative insert, it's actually plowing that material. Again, in this area here, on the negative insert, you're given your opportunity to create heat, which is something we do not want to do in heat resistant materials. Again, the heat will go back into your chip. It does not go back to your chip. It actually goes into your insert and will create great amount of challenges for you on your component and or your insert, which will affect your process security. So when it comes to these materials, one of the things we need to look at is the surface speed. We talked about that on the titanium slide earlier. Speed will be your killer. What we want to do is look more into the engagements that we're putting our tools through and our chip load. We want to be a little more aggressive with those. Speed will be the killer. If we create too much speed, we create too much heat. So we want to create a balance there. In the milling operations, we want to try to add as many teeth as possible to be more productive, as opposed to turning, which of course is just a single insert. So we want to try to keep our engagements a little bit on the light side and keep our speeds on the lower side as best we can. Next, we want to look at the tool wear. What type of typical tool wear do we get when we're machining these types of material? Frankly, the most common is going to be our notch wear. Is typical on the depth of cut we're running our insert. So what happens is you get a little heat propagation area right here. And what happens is you get that buildup of heat right there, and that's what creates the notch. Eventually, that notch will turn into a whole edge line breakage. So we'll talk about techniques later on which could help avoid this. Some things we can do, of course, is we can change the type of inserts. We'll go into a little more detail later on. Maybe a round style insert, we can change our lead angle. When we look at an insert, for instance, that comes in on more of a 90 or 95 degree angle, what happens is we have a lot of heat buildup, and we'll go into more detail with this later on. And we want to try to avoid that as much as we can. We can try to keep it below the nose radius of our insert, which essentially gives us similar to a round insert or a button type of insert. We want to try to use more of a positive reinforced geometry, something sharper. Again, less tendency to build up that heat as opposed to the negative inserts. And we'll see this more in harder materials, of course, because being harder, they're going to generate more heat while we're trying to machine them in the operations. And also the material conditions will be a factor as well. The forged and cast are typically a little more on the abrasive side. Hence, you'll see a little bit more of a wear mechanism creating more heat. So this could be an issue for you as well. The other thing to look at is go to actually a thinner grade, something along the lines of a PVD type grade opposed to a CVD grade. What happens, it's the thinner coating, therefore it has a better shear tendency and a sharper edge line. The other type of wear mechanisms you're going to see quite often is going to be your plastic deformation. And that's essentially what happens is you're heating up that insert to a point where the insert is actually starting to melt. So in the case here, you can get an impression or a depression. Depression is more something that's hitting it actually, whereas an impression you might see maybe in a grooving type insert where it's actually pushing into the insert and creating an impression of the insert. And here we might want to look at something more of a wear resistant grade, a harder grade. You want to reduce your cutting speeds. Again, use that more positive geometry to create a shear effect. Or decrease your feeds, because the feed sometimes adds a lot of heat as you're shearing the material. So be cautious with this. The other thing is sometimes you get these types of wear mechanisms, but we don't stop the insert earlier enough. So essentially what happens is you'll get a whole edge line break. And what you think might be happening is, oh, I'm just losing my edge because it's not tough enough. And then you'll change it to a tougher insert. The fact is you should actually go to a more wear resistant or harder insert. To compensate for this plastic deformation. So what we want to do is make sure we're stopping our insert before they get to the final failure, so you can read the wear properly and make the proper adjustments. The last one we're going to take a look at is actually thermal cracking. More or less common in milling operations. Reason for milling is essentially a cyclical operation. And what's happening is what you're getting is a shock to the insert. So when you're dealing with these materials, one of the things we do is we want to run copious amounts of coolant. High pressure is better, which we'll talk about later. And the reason for that is to try to evacuate that heat as best we can. The challenge we have when we're doing milling operations, as I mentioned, it's cyclical. It's in and out of cut, in cut, out of cut, in cut, out of cut. And what we're doing is actually we're shocking the insert with that coolant. So it's almost taking an ice cube and throwing it into a warm glass of coffee or tea and watching it shatter. The same thing is happening to your inserts. So some of the things you could do is find ways of stabilizing the temperature. You can select a tougher grade, something with a tougher edge line, which is essentially more or less a PVD style grade that will compensate for that. But these are some of the challenges you'll have when you're dealing with milling operations in these types of materials. And again, sometimes what happens is we push the inserts to failure, and what happens is we have a whole line, edge line that is actually gone, and we think we might have microchipping, or we think we might have edge line failure. The fact is, what's happened is we're actually getting a thermal cracking or comb cracking. So again, we need to stop the inserts prior to complete failure, read the wear, and make the adjustments accordingly. So some of the things we could do to help compensate the challenges we have with some of these wear mechanisms is we can change our entry angles. Sometimes the feature we need to machine is conducive to what we need to do, i.e. if we're going against a shoulder, we're going to need a square shoulder type of insert. But one of the things we can do to try to compensate some of the challenges we're going to have is change the entry angle of your inserts to try to thin out those chips. And we'll go into that in more detail. There's a gamut of styles of inserts out there to choose from, and each one of them has their need. Anywhere from, we mentioned, a 90 to a 95, typical on a square shoulder mill cutter, or a C or a D&MG style insert for going up a wall. Just be mindful when you're running these, we're going to be more prone for notching type operations. As we put the more of an angle on the insert to 75, 60 to a 45, you'll notice we're actually thinning those chips and we're elongating the contact area. What that does, it dissipates the heat over a longer area, and we'll get into that a little bit further. So one of the best ways to look at dissipating the heat is ideally about a 45-degree entry angle, or a button cutter with a depth of cut that's about similar to a 45-degree entry. So what happens is you actually here, you can see the bottom of the graph right here, the chart right here, is this is actually the contact area of the insert. So if you're going to take about a 90-95 degree entry angle insert at a depth of about 80 thou, the contact area is about 80 thousandths of an inch. So what happens is all that heat is put into that specific area. But as we tilt those inserts, you can actually see we elongate that area. So the heat actually is over a larger area, which in essence gives you an area where we can dissipate the heat a little bit easier, relatively speaking. So what we want to do is, when we can, try to use inserts that are 45 or button style, with using a button style, an entry angle pretty much close to about a 45 degree, which we'll touch on shortly. One of the things you need to be mindful of is we need to change our feed. So as we put the insert on an angle, what we're doing, we're thinning those chips. So what happens is, as you tilt to a 45-degree angle, we got to keep in mind that that chip is now at about 70% as it was on a 90-degree. So there's got to be some considerations taken, and we'll go into that a little bit later. One of the things we do not want to do is underfeed our inserts. If we do that, we're not shearing that material anymore. We're actually rubbing those materials. And essentially, it's like if you take your hand and rub it on the table, it creates heat. It's creating friction. You're doing the same thing on these materials. And the challenge is, again, these materials are heat resistant. They are designed to resist heat. That heat's going to go back into your insert and create an unstable situation for yourself. So here's a good example of several inserts. The only difference is basically the geometry and the entry angle. If you look at the insert all the way to the left, This is a typical CNMG, and you can see here, we're getting that notch actually developed right here. That is that heat propagation area based on the depth of cut. And as you see, as we steer the insert of more of an entry angle, you can see on an SNMG at a 75 degree, we still got quite a bit of flank wear. That's because of the heat buildup in the cutting zone. But as we change that entry angle to a 45, you can see that's a lot less. And we've actually brought that area that we were talking about earlier is elongated. So we're dissipating that heat over a longer area. As you can see here on a button insert, same thing, very similar to the SNMG style insert. We're making that area a lot longer, again, dissipating the heat. All these inserts here are run at the same criteria, 80 thou depth of cut, 10 thou feed, 160 surface feet, all for about 5 minutes. And all we did was change the entry angle of those inserts. And you could see this from a notch wear all the way to a 45-degree style entry angle. You can see the process security you're now going to have. Again, if you're going up against a shoulder, it's a necessity to use a CNMG style insert as opposed to the others, but just be mindful of the challenges you're going to have. Here's another nice picturation of the different inserts. Again, you can see the CNMG up at the top with the notch wear. Again, a 45-degree angle, and again, a button insert. The thing I want to take note of is we talked earlier about the chip thinning, which we'll go over in a little more detail in a moment. But you can see it from the cutting data. We're running essentially all the same surface footage. We're actually running basically the same feed, but what we're doing is we're compensating with chip thinning effect. So you can see here on the CNMG, we're running a 10 thou feed. When we're looking at tilting the insert like a CNMX here on a 45, we've actually increased that by a percentage of about 40%. So we're actually increasing our feed, actually increasing our productivity based on the chip thinning. And you can see here on the button cutter, we actually increased it substantially more, up to 20 thou. The insert is still seeing the same amount of chip thickness, but because of the chip thinning, we're actually gaining that productivity, so we're not underfeeding. And you can see here what happens is we're going a cubic metal removal rate of about 7 inches to a button or a 45 degree entry insert to 13. So we're almost doubling our productivity. And you could see it took us 5 minutes to do this, opposed to 4 minutes to double our productivity. So please keep that in mind. So anytime you're using these inserts, we need to take in serious consideration the chip thinning effect it takes, but look at the amount of productivity you're gaining and also process security. So when we look at the chip thinning effect, we'll look at this for round inserts, for instance. You can see here, if we were to change our entry angle based on our depth of cut, and the example here we're going to show, if we took the ICD insert and took about 15% of the ICD insert, our entry angle is going to be around 45 degrees, which is very similar to a 45-degree SNMG style insert. So our feed modification factor is going to be about plus 40%, about 1.4. So what does that mean? So if I'm feeding this insert and I want to see a chip thickness of about 4 thou, I need to increase my my feed rate to be able to see that 4 thou chip thickness. So we need to increase our chip thickness up to 6 thou. If I'm going to run an HEX or a chip thickness of 14 thou, I would need to change my feed to 20 thou. Reason being is for that chip thinning effect. Again, if we don't do this, what's going to happen, we're going to underfeed those inserts, and we're actually going to push the chips, creating heat. These, again, is something we desperately want to avoid. And again, if you do that, if you don't do that, you're actually being detrimental to yourself, not only creating the heat, unstable operations, but you're leaving productivity on the table. Again, most ideally is about a 45-degree entry angle. So if you're going to use an instance of button cutter, a good rule of thumb is to be about 15% of the IC of the insert, which will give you that around a 45-degree entry angle. So next thing we want to be mindful of as the inserts are running. So if you see here, the round yellow circle is actually your insert. Anytime we're going up against a wall, we need to be mindful that we're actually going to change that arc of engagement on those inserts. So we need to be very careful with our programming techniques. So for instance, if you're coming up against a wall, you need to be cautious that as you enter this wall or this corner, and we're machining up against it, either coming down across side or coming across the floor, what's going to happen is we're going to get this wraparound effect. And you're actually going to overexert the insert. These are the areas we're going to get a tremendous amount of vibration, going to get a tremendous amount of heat buildup. You're going to get very ugly swarf or chips, very hard to get out of there. You're going to have challenges breaking those chips, which is already indicative of these types of materials. So one of the things you want to do is be mindful of that and come with different insert ICs based on the radius you want to go against. So a good example of this is if here we want to program a radius of about 25% of the IC, the insert. This will give us an entry angle of about 70 degrees. But better yet, if we can have our IC at about 50% of the program radius, that's even going to be even better. And what's going to happen is we need to adjust those feet slightly in those corners, because if you recall before, we were at 15% engagement, and as we entered this radius right here, creating this corner, again, that arc of engagement is going to increase. We still need to be mindful of adjusting our feeds accordingly, because we saw that chip thinning effect. That's going to be lessened as we approach those corners. So we need to make those adjustments. But just be mindful that anytime we approach these corners, we need to properly adapt the insert size to the radius we're going to be creating in our feature. Other techniques we can do is we could do different types of dynamic or trochoidal techniques. It's nice today because a lot of the software, CAM software packages offer these solutions for us. Whether it's dynamic or adaptive or waveform, everyone in the market today has something, so it makes it very much easier for the programmers today in the industry. So what we mean by that, instead of plowing straight down into the walls and going across, we do these nice radial sweeps in and out. The other nice thing is what you could do is you can go across in one direction on a round insert and back the other direction with the insert. What does is it's nice because you're essentially cutting on one side of the insert and the other side of the insert. So what's happening is you're given one side of the insert time to cool as the other insert's in engagement, and then vice versa. What that does is it helps with that heat propagation area that we saw earlier on those 90 degrees style inserts. Other techniques we could do, not as beneficial, of course, as this sweeping technique, but ramping techniques. We can also add an arc to these ramping techniques if need be. The idea for these ramping techniques is we're changing our depth of cut as it's actually approaching into the cut. The challenge of this is your arc of engagement is changing as you're plunging down into the component. So your feed needs to be adjusted as you're going into your feature. So that's something you just need to be mindful of. So dynamic, adaptive types of techniques work extremely well for these types of features. Other techniques we could use too will be if we're sweeping down a wall. So what we could do instead is we break the feature up into two parts. Part one would be, of course, to come down the wall. And the second part would be to come back up the wall, sweeping, doing the floor. So we can break this into two different sections. Again, being mindful, we want to arc down at the bottom. Again, we want to maintain that radial engagement. We don't want to go down to our near net shape. We want to stay away from that floor slightly and then come back later on. You can see in the animated picture below, we want to come back from the bottom and back up again. Now, sometimes this might take a little bit longer when we're making our components, but we need to be mindful, though, the process security we're going to have. So next, I want to talk a little bit about the coolant. These materials have a great amount of challenges with breaking chips. So one of the things we want to talk about a little bit is using high pressure. Using the high pressure actually creates a hydraulic wedge between your insert and the chip, helping you force it to break. Many of you have machined nickel-based materials, of course, and the titaniums, and we know the challenges when we're turning these materials. So you can see here from the different chip chart we have here is utilizing a non-high pressure tool with a high pressure tool. And you can see here using the standard or low pressure, we'll call it, and using high pressure. So the material here we're actually machining is titanium 6Al4V. And you can see here the types of chips you're going to get using standard pressure as opposed to the high pressure you're using here. So if you're having trouble with the bird's nests and things of that nature in the titanium, using high pressure upwards of about 80 to 100 bar will work wonders for you. It works better with titanium than nickel materials, but it still will help with the nickel materials. And you can see here with an example too, utilizing the normal pressure and then increasing to about 80 bar, about 1100 PSI. You can see the difference in tool life here. You got that heat that's built up in the cutting zone. That pressure is helping bend the chip essentially back off the insert slightly and cooling down that zone. So you can see your normal pressure after 10 minutes, after 20 minutes, you can see a tremendous amount of notch, a lot of thermal activity in here. And then you can see here, same insert, same cutting parameters. All we've done is increase our pressure. You can see here up to about 40 minutes of tool life we've gotten, and we're just starting to see a notch build up. And that only thing we've done here is change the coolant pressure. And again, in this other chart, you can see here the different depths of cuts we've applied. You can see the bottoms of these charts actually shows normal pressure as opposed to the high pressure on the top. One of the things I recommend too is you can see here, these are chip charts. Find out optimally where your sweet spot is in your material. You know, how's it going to function on your machine, the different material you have, and come up with a chip chart and kind of circle that area that's best for you in your shop, in your application, and stick to it. And of course, utilize the high pressure coolant. The other thing I just want to mention is when cutting titanium, please always use coolant. You do not want to machine titanium dry. It'll create what we call an exothermic reaction and create a potential fire that's very difficult to put out. So I just want to urge everyone to be mindful of that. Next, I like to discuss the different types of machining strategy. I think this might be a good time for another poll question. Heidi, can you help us with that? So the next poll question is going to be, where are your biggest challenges? Is it the materials? Is it your application, your CAM knowledge? Is it tooling knowledge? Is it finding resources, engineers, operators in today's environment? What's the biggest challenges you see today? As we wait for that poll question to come in, I will continue with our presentation.
There are about 15 seconds left.
Excellent, thank you very much.
And here are the results.
Here is it. Okay, so it looks like the majority of people, okay, material knowledge and all the above. Okay, very good. Thank you for that. So one of the things is so critical is we call this our golden rule. When we are in a milling operation, we want to make sure the process ensures the lowest chip thickness possible when exiting a cut. It is very important to do that. We always want to have a thick to thin chip. That should be our mantra when milling. So in essence, what's happening during an operation, we have a cyclical operation as the inserts are spinning in a milling cutter. And as it goes in a cut, we create a thick chip and thin chip on exit. The problem is if we have a thick chip on exit, and you can see from the animation right here, the yellow being the insert, we get a tremendous amount of tensile stresses right here. What happens is we actually break out. When we break out, what will happen is actually the insert will actually fracture an edge, and we want to be very careful of that. So what actually happens is the milling cutter orientation actually gives us that chip thickness. So whatever happens, whenever you're doing a full slot operation, we get a thin to thin chip. This is one of the most challenging applications when it comes to milling, especially in these heat resistant materials. If you think about it, we're having a thin chip on entry, building up a chip, and then thin chip on exit. What happens is we're not actually creating a chip here yet. We're actually rubbing that insert as it progresses in. The other challenge we have is if we do 50% of the cutter, what happens is we're actually taking an insert and slapping it against the side at the full chip thickness, which actually creates challenges. And then what we want to do is we want to try to keep our cutters engaged at around 70% or less than 50. So if you look at our animation here, you can see what happens. And what's going on here, you can see in the cut here, we're actually building up our heat as we're progressing in the cut. What we want to do, we want to shift our cutter in about a 75%, 70% engagement. What happens is we get about 60 to 70% of the chip thickness on here. We're easing into cut, and what we're doing is we're creating a chip. We're not actually rubbing the chip as it gets engaged. We want to make sure we actually offset in the right direction. If we offset in the wrong direction, we're actually doing a counterproductive, and we're actually thin to thick, which is happening is we're actually rubbing and then exiting on that thick chip, which we don't want to do. The other thing we want to try to do is we always want to try to down or climb mill when we're machining these materials. We want to create that chip. If we do an up or conventional mill, what we're doing is actually rubbing the chip as we're starting to engage and then creating that thick chip on exit, which is exactly what we want to do, which will create failures for us and create challenges for us. One of the things we want to do is we want to try to roll the cutter into cut as we enter a component. This gives us a nice smooth entry. You can see here as we enter a component, we get that thick to thick chip until we start to get engaged, which we don't want to do. That creates a lot of challenges. A lot of times you'll hear the cutter make that pounding noise as you're getting into the cut. Can ideally reduce your feed as you enter the component, which can work. What we recommend you do is actually roll the cutter into cut. What this does, it creates that thick to thin chip, very stable operation. You do not need to reduce your feeds as you enter the component. A lot more secure process. As you can see from the animation. We want to be careful not to roll in the wrong direction. It'll be what'll happen is you'll get that thick to thick chip like we talked about earlier, and create challenges for us. See it here from the animation. Insert into cut, we get our chip thinning effect, reduce our vibration, much better predictability, much better tool life. And you can see here from the examples on the screen, the first example, straight in versus roll in 718 Inconel. After 2 passes, you already got your edge line failure, a lot better process security after 15 passes. And that doesn't only work in some of your more exotic 718 type materials, but also in 316 stainless, some other 300 stainless materials, as well as some tool steel here. And you can see a lot better process security. Now we understand sometimes there are challenges when it comes to maybe fixturing, features on a component. So one of the things you can do also is you can bring your cutter in at about a 20 to 30 degree angle, and the same effect will take into place. Again, this will be a lot less vibration. It gives you that thick to thin chip on entry, a little bit easier to program. And again, if there's maybe a fixture or a feature you can't obtain with the roll-in technique, this is another way to go about it. If you can't, we recommend reducing feed as you enter the component, and then once fully engaged, then you can increase your feed.
Hey, Bill, this is Chris.
Yes, Chris.
While we've got a few questions from the audience, I think some are a little bit more general in nature, and we can move those towards the end if there is time. And then I think a more specific question came up that might be worth addressing now.
Sure.
But one of the participants had asked, what is a good rule of thumb for roll-in arc radius to cutter radius ratio?
Essentially what you do, you take the radius of the cutter, multiply it by 2 as your radius, your offset from your component, add that to the radius, and that will be your roll-in.
Thank you.
You're welcome. So again, it's 2 times the diameter of the radius of the cutter. Whatever your offset is, 100 thou, 80 thou, 50 thou, whatever it is, add that in there, and that will be in your arc of engagement for your roll-in. Just go back to that animation. Okay, so thank you for that question. So the other thing we want to be mindful of is keeping the cutters engaged at all time. You can see here from the animation as that cutter goes in and out of cut, what's happening is every time we enter that component, you're creating an area where it's prone for vibration, that thick to thin chip we talked about. We want to try to keep our cutters engaged at all times. One of the things we want to be mindful of too is every time we change direction with our milling cutter, we want to create that arc as similar as what we did when we did that roll-in technique. Reason being is we're going to get that chip effect or that roll-in effect with that thick to thick chip as we talked about earlier. The other thing we want to be mindful of is interruptions in the components. There are always holes, features in the different components we need to machine. So what we want to try to do is try to roll around them as best we can and program around them. Again, using the roll techniques to go around those. Again, when we change direction, anytime we do sharp angles and change in direction, inside the component itself, we're going to get that thick to thick chip. Making that arc in there, we'll get that thick to thin chip, and it'll be a lot better process security. It'll sound better. You'll get a lot better tool life. And staying on the component is very important as well. Every time we exit, we go off the part and back on the part is, well, we're not making chips or we're not being productive. And every time we come off and on and engage the component again, we give ourselves area where we can have challenges with the chips formation, as cutter engagement, as well as areas where we could have chipping of the inserts. So we want to be very careful of that. Next, I want to talk about is a little more in depth about the chip thinning. We touched on it with the turning. Now I want to talk a little bit more on it when it comes to milling operations. So the entry angle of a milling cutter, looking at a 90-degree, your chip thickness and your feed are essentially the same. As we tilt that insert, like we said in turning, again, we have a chip thinning effect, and what we need to do is increase our feed to maintain that proper chip thickness. So if you take a 90-degree, a 45-degree, and a high feed cutter and run them side by side, essentially what happens is we're going to get a chip thinning effect. So what happens is we need to increase our feed in order to maintain the proper chip thickness. So if you take a 90-degree cutter, for instance, your chip thickness and your feed are identical. You have a factor of 1. And as we stated earlier, when it comes to a 45-degree, we actually have a 40% increase in productivity. So we need to increase that by a factor of 40% or multiply our chip thickness by 1.4, which would be our feet per tooth. Now with round inserts, as we talked earlier, it all depends. And we'll talk about that in a moment. And when it comes to, for instance, a high feed, something on a 10-degree angle, we can actually feed that on a factor of almost 6 times. And I'll actually show you how to come up with that calculation. However, when it comes to buttons, we need to be mindful of the depth of cut is going to determine what our chip thickness is going to be and how we want to address that. So when we look at buttons, for instance, the depth of cut is going to be the driver of how we need to increase our feed. So for instance, as we lower our depth of cut, the radial engagement on that insert decreases. Therefore, we can almost run those button cutters as we would a high feed cutter, for instance. Therefore, we can actually increase our feed per tooth, almost running it like a high feed as opposed to bearing a cutter on a larger depth of cut. Again, if we don't do that, we will have a tendency to underfeed and create that wear again and that pushing of the chip. So how do we calculate that? It's very simple. We basically take the sine of the angle of the insert, take its reciprocal, and that will be our feed modification factor. So if you have a high feed cutter with a 15-degree entry angle, for instance, we take the sine of 15, which is 0.2588. We take its reciprocal. Your feed modification factor will be 3.86. So basically what we do, if you have your feed per tooth of whatever it is, you multiply it by 3.86, and that will be your chip thickness. Other thing to take in consideration is your radial engagement of your tool. So you also have a chip thinning effect with your radial engagement, and you need to be mindful of that. So just like your insert engagement, your cutter engagement also is important to notify because you can actually underfeed your cutter as well. So If you have anything less than half the diameter of the cutter itself, you can actually increase your feed on your tool to maintain that chip thickness. Now, one of the things you need to be mindful of is if you have something with an entry angle, as well of a small radial immersion of the cutter, it's a twofold effect. So not only can you add the factor of a feed modification factor for your insert, you can also do it for the radial engagement. This is something that's very often missed and very important. So you do not underfeed those inserts. So be mindful. You have two feed multiplication factors there: insert entry angle as well as your cutter immersion. Next topic I want to talk about, which is pretty common in titanium machining when it comes to the frame industry, is high feed side milling. So we touched on it just on the last slide when it comes to the radial immersion of your cutters. This is essentially what this is all about: light radial engagements. The idea is typically you'll see this on long edge cutters. You could see it on your solid round tools, but essentially what you want to do is you want to try to reduce this arc of engagement. This is an area where you have a lot of heat buildup in the cutting zone when it comes to these types of materials, which we've learned that it is not good. So we want to make that area a lot less. So you have your high feed capabilities because of your arc of engagement. You have a less area for heat propagation. So that's the idea with this. So just like I had mentioned on the last slide, anytime you're looking at something with full arc of engagement, you have a lot of heat buildup in here. And again, these are heat resistant materials. On the lower radial engagements, we have a less tendency to have that heat propagation area. So it's a lot better for the inserts, a lot more secure process. And again, these materials are heat resistant. This is going to be an ugly situation as opposed to this. So some of the techniques we could use for this is take a pocketing exercise, for instance. We saw this actually on one of the animations when we kind of did that box method, I called it. So every time you come into a corner and change your engagement, you can see here in this animation that you have this larger arc of engagement. This is an area where you're going to get a lot of vibration. You can get chipping of the insert. So we want to be mindful of that. If we can keep a continuous low radial arc of engagement in the spiral morph kind of application, you have a lot better process security, a lot better predictability. And here's some actually science behind it. So if you can look at the two different types of techniques when we're machining here, this is more the box method, here's more the spiral morph. You can actually see here the forces that are generated. So on the first top one, you can see you're getting forces upwards of over 1,500 newtons. As opposed down here doing a spiral morph, we're getting under 800. That's a lot better for the tools. It sounds better, less areas for vibration, a lot better predictability. And you can also increase your data. And you can actually see here from this animation here what actually happens in the corners. Spiral morph, very even, very nice, predictable tool life. As we do this box method, you can see here what happens in the corners. We get a tremendous amount of forces, vibration, very ugly, tendency of chipping. We need to reduce our feeds in the corners, a lot less process security. So some of the things we can do if we are kind of handcuffed in doing this is we need to, just like the inserts we saw in turning, we need to optimize with the different types of engagements radially in the corners. Ideally, you want something that's about 25% of the diameter of the cutter, but better yet, we can actually reduce that with a 50% reduction, and that will give you a lot better predictable tool life. We just want to be mindful of the feed changes in the corner. So every time we hit the corner, because of this arc of engagement, we need to reduce our feeds in the corners to compensate that. That's why many times that spiral morph we just saw is a lot better. Now, if you need to do corners, which we have to, one of the techniques we can utilize is a slicing technique, where instead of driving the corners, creating a large radial engagement, we can create a slicing technique, minimizing our engagement as we continue into the corner, optimize with the diameter of the cutter. And as you go into the corner, you get a lot better process security. Again, takes a little bit more time. You'll get better tool life, better predictability, better surface integrity. Next, I want to talk a little bit about the exotic materials we see in the industry. I'm just today going to touch on the ceramics. There are others out there, CBN and PCD, which I will not touch on today, but I just want to touch briefly on ceramics. I do want to note right off the bat, do not use ceramics in titanium. You will get a fire you cannot put out. So be mindful, ceramics should only be used on nickel-based materials only. So
Hey,
the
Bill, just a quick
yes,
time check. We've got
sir.
about 5 minutes left.
Okay, thank you, sir. So these are a little bit different when it comes to the carbide. We can run at elevated temperatures. We're typically in these, say, nickel materials, we're going to run anywhere from 80 to 150 surface feet. You can see here in turning applications, we can run up to about 1200, a lot better predictability, a lot better productivity. When it comes to the milling operations, we can run in excess of over 3000. We actually want to put these materials into a molten state to be able to machine them. Some of the toolware we need to be mindful of when it comes to the ceramics is a little bit different. We have a tendency of getting a top slice. Top slice is typical to overfeeding those inserts and actually creating tensile stresses on the top of the ceramics, which will essentially pop that off. So what we want to do is we want to be mindful of our feeds and actually reduce our feeds on those if we can, or go to a stronger whisker reinforced grade. And again, just like we talked about the different techniques to avoid notch wear in carbide, same goes for the ceramics. You know, those different radial engagements, reducing feeds, creating sweeps, changing depths of cuts on the inserts, all will help with the notch in the ceramics. When it comes to milling, one of the things we do not want to do is underfeed those inserts. We actually are under speed those inserts. We want to make sure we have a high elevated speed. Again, we're trying to get these materials into a molten state. So it's actually almost like it's on fire to be able to remove those materials. So if you create too low of a speed, you're not going to get good tool life and not good predictability. The other challenge when it comes to ceramics is it does not like to go up against walls. So if we're creating features up against a wall, we want to use carbide first to clean it up, then go in with ceramics. The other thing is we talked about climb cutting when we're using the carbide. When it comes to ceramics, we want to do just the opposite. We actually want a conventional mill. We want to build up that heat to create that plasticized state of the inserts. You can actually see here from the different examples here, we're actually getting top slice because we're creating too much pressure on the left as we are on the right. We're getting nice even wear. Okay. And again, when we're doing the roll-in technique, we want to do the opposite we did when it comes to the carbide. And again, same as I said earlier, half the diameter cutter, and then add on whatever your offset is for the cutter. The other thing is with coolant, we do not want to run coolant when it comes to ceramic milling. However, we do want to run it when it comes to turning. So milling dry when it comes to ceramics, turning wet when it comes to ceramics. Very important. If you haven't seen it before, here's just a quick video of some ceramic milling. This sometimes is intimidating and makes customers a little nervous. This is very common, you will see in ceramics, so please do not be alarmed by that. Okay. And lastly, I just want to say, think about change. I went over a lot of topics. There's a heck of a lot more to talk about when it comes to these exotic materials. Please reach out to your either your Sandvik rep, your Sandvik Coromant rep, or your MSC rep, and we can work with you on these different techniques. Think about change. A lot of people don't like change. Now is the time to think about it. We have, a lot of times we might be on a slower production today, with some of us unfortunately on furlough or have some time off. So think about change. What can we do in your shops to help increase productivity, give better predictability, and better efficiencies? So thank you everyone for your time.
Thank you, Bill. This is Chris. And with that, I would say, while we did get a few questions from the participants today,
okay,
so we don't have to rush through those, we will plan to address those individually and contact the participants that submitted them directly. And I would just add on to your comments there to say thanks to everyone for your time and participation. And William, thanks to you and the Sandvik Coromant team for working together on today's webinar. Also, we will be posting a recording of today's webinar on our site, mscdirect.com/bettermro, in the coming days. And with that, we will go ahead and conclude the webinar. Thank you, everyone.
Thank you, everybody.